In today's video lesson, we're going to review acids and bases from our prior knowledge. So acids have a lot of properties in common. So an acid produces hydrogen ions or protons in the form of hydronium ions in water. They taste sour. Now, we wouldn't want to taste every acid that we come across, but like the ones that are edible, lemon juice, vinegar, citrus, they're all sour tasting. We can infer that all acids are sour tasting, but I don't recommend tasting them. Acids corrode metals. They are electrolytes, so they conduct electricity because they dissociate into ions. They react with bases to produce a salt and water in a neutralization reaction. And acids have a pH of less than 7, so anything lower than 7. And they turn blue litmus paper red. So one way of helping you remember is blue to red is acid. Kind of rhymes. Now, bases produce hydroxide ions when dissolved in water, and they taste bitter or chalky. If you've ever had, baking soda plain, it's very bitter tasting. Or if you've ever had the misfortune of eating soap, same thing, it's bitter tasting. So bases are bitter. They also are electrolytes because they too dissociate into ions, and that allows the solution to conduct electricity. Bases feel soapy or slippery, so that's why soap does such a good job, because it is slippery. If you've ever had bleach on your hands, if you've ever spilt a base on your hands will feel very smooth and slippery, so that helps you identify that you maybe need to get that off your skin. Bases react with acids to form salt and water in neutralization reactions, and bases have pHs of greater than 7. And they turn red litmus paper blue, so I always think blue for base, and that helps me remember how litmus changes in the presence of base. So the Arrhenius definition of an acid is a substance that produces hydrogen or hydronium ions when placed in water. So here's our example. So hydrochloric acid plus water makes hydronium ion and chloride ions. A base, according to this rule, is a substance that produces hydroxide ions in water. So ammonia plus water makes ammonium plus hydroxide. So the Bronsted-Lowry definition of acids and bases is that acids are proton donors and bases are proton acceptors. So when we look at this example, we have ammonia. It's going to accept a proton from water. So it's going to be the base and water is going to be the acid. With this definition, a base will always have a conjugate acid and the acid will always have a conjugate base. So ammonia is a base and it accepts a proton from water, so it becomes ammonium. So it accepted a proton to become NH4 plus. And then water is acting as the acid in this example, so it's going to donate its proton to ammonia to become the conjugate base hydroxide. So we can always label these acid-base pairs. So now we're just going to check our understanding. So in our first example, we have sulfuric acid with water becoming hydronium ion and hydrogen sulfate. So in this example, this H2SO4 is the acid, and then it is giving up a hydrogen or a proton to become the conjugate base. And then water is acting in this case as the base. And the hydronium will be the conjugate acid. That's how we would label this first example. In our second example, we have hydrogen carbonate reacting with water to form hydronium and carbonate. So in this example, the hydrogen carbonate is acting as the acid, and that would mean that the carbonate would be the conjugate base. And the water in this case is acting as the base because it's accepting the proton from hydrogen carbonate. So this would be the conjugate acid. So there's that one labeled. And our final example, we have hydrogen chloride reacting with water to make hydronium and chloride ions. So in this case, this is the acid. And this is the conjugate base. And the water in this case is acting as the base again. So in all three times, water was acting as the base. And then this is the conjugate acid. Like so. Under the Lewis definition of acids and bases, a Lewis acid accepts an electron pair, and a Lewis base donates the electron pair. So in this example, water is acting as the base, and it's donating an electron pair to a proton, which is acting as the acid, to form hydronium. Now we'll review the pH scale. So the pH scale is a way of expressing the strength of acids and bases. And we use this scale because if we were just using the molar concentration of hydronium or hydrogen or hydroxide ions, we would be using really small negative powers of 10, which is hard to manipulate. So instead we use a logarithmic scale to help us use numbers that are much more easy to use. So acids, have really low pH, so pH of 1 versus 2, that means that the pH or the concentration of the acid is 10 times stronger or higher. So we'll just move from there and talk about how we can determine pH. So we calculate pH by taking the negative log of the concentration of hydrogen ions or protons. So to find the first example, the pH of a 0.15 moles per liter solution of hydrogen chloride or hydrochloric acid, remember pH equals negative log the concentration of hydrogen ions. So it's going to be equal to negative log 0.15. And that is equal to negative 0.0 or 0.82. Or just when you cancel out those two negatives, the pH is 0.82. In our second example, we're trying to find the pH of a 3.00 times 10 to the power of negative 7 moles per liter solution of nitric acid or HNO3. So pH again is equal to negative log of 3 times 10 to the power of negative 7. And that is equal to 6.52. So that's the pH for the second one. So we can manipulate that relationship because we know that pH is negative log the concentration of hydrogen ions. To find the concentration of hydrogen, that's equal to 10 times to the power of the negative pH. So in this example, we're to find the concentration of hydrogen ions if the pH of Coke is 3.12. So we'll take the anti-log of both sides, and we can get 10 to the power of negative pH is equal to the concentration of hydrogen ions. So the concentration of hydrogen ions is equal to 10 to the negative 3.12, which is equivalent to 7.6 times 10 to the power of negative 4 moles per liter. So water undergoes autoionization. So what that means is that water dissociates, and then some will become hydronium ions and some will become hydroxide ions. So it can actually function as both an acid and a base. So the equilibrium constant for water is known as Kw, and it's equal to the concentration of hydronium ions times the concentration of hydroxide ions, which is equal to 1.0 times 10 to the power of negative 14 at 25 degrees Celsius, or 298 Kelvin. So in a neutral solution, the concentration of hydronium is equal to the concentration of hydroxide, which means that it's equivalent to 1.0 times 10 to the power of negative 7 moles per liter, which if you were to find the pH from that, it's equal to 7. So calculating the power of hydroxide. So because acids and bases are opposite, so are the pH and the pOH. But pOH doesn't really exist. Instead, we use pH as our value to tell us how strong an acid or a base is. But we can use the calculation for finding pOH and then converting back to find out what the pH of a substance is. So because pH and pOH are on opposite ends, pH plus pOH will equal 14. So the power of hydroxide is equal to the negative log of the concentration of hydroxide ions. So in this example, we're being asked, what is the pH of a 0.0010 moles per liter sodium hydroxide solution? So we can find out the pOH, which is equal to negative log of the concentration, so 0.0010, and that is equal to 3. Now, we know that bases don't have a pH of 3, so this is the reverse. So to find the actual pH, that's going to be 14 minus 3, so it's equal to 11. Or, that's one way of solving. You could have also used the equilibrium expression. So Kw is equal to the concentration of hydronium ions times the concentration of hydroxide ions. And then you could sub in our value. So if you put in the 1.0 times 10 to the power of negative 14 divided by the concentration of hydroxide, which is 0.0010, that's going to give you the concentration of hydronium ion, which is equal to 1.0 times 10 to the power of negative 11 moles per liter. Once you have that value, you can put that into the pH calculation. So pH equals negative log of that value, 1.0 times 10 to the minus 11. And that's going to equal 11.00. So we can get the same value two different ways. Okay, so in this example, we're being asked to find the pH of a 2.0 times 10 to the power of negative 3 moles per liter nitric acid solution. So nitric acid is a strong acid, so we can assume that it's going to 100% dissociate into ions. So in this case, our concentration will be, of the hydrogen ions, will be 0.002 moles per liter. So we can just plug those values in. So that is equal to negative log of 0.002 moles per liter So that is equivalent to 2.7. So that's our pH for this one. Okay, so for this example, we're looking at finding out what the pH of a 1.8 times 10 to the power of negative 2 moles per liter barium hydroxide solution. But there's something you need to note here. In this example, we have 2 hydroxides for every 1 barium. So we need to find out how much hydroxide ions we are going to end up with. So it's a 2-to-1 ratio. So that tells us, and this is a strong base again, so it's going to 100% dissociate. So we actually have 0.036 moles per liter of hydroxide ions. So 2 for every 1 molecule of base. So we need to plug in that value for our pH, or our POH first. So POH is equal to negative log the concentration of hydroxide ions, so it's equal to negative log 0.036, and that is equivalent to so that's equivalent to 1.44, but we're not finished. We need to know the pH. So pH is equal to 14.00 minus 1.44, and that is equal to 12.56. So that's the pH of this solution. So the strength of an acid or base depends on its ability to ionize. So strong acids almost completely dissociate into ions. So here would be an example. So hydrochloric acid almost completely dissolves into hydrogen and chloride ions. So the hydrogen ion, the proton, will combine with water to make hydronium ion, but it has completely dissociated. Weak acids, on the other hand, do not fully dissociate into ions. So a good example of a weak acid would be acetic acid or ethanoic acid. So not all of it will dissociate into ions. And we'll learn more about what that means and how we will involve that in calculations with acids and bases in our next video. Strong bases also almost fully dissociate into ions, and a really great example of a strong base would be sodium hydroxide, and it dissociates into sodium ions and hydroxide ions. Weak bases, on the other hand, don't fully dissociate, and a great example is ammonia. Ammonia does not fully dissociate into ammonium and hydroxide.